Welcome to today's Friday Forum. My name's Kelly. I'm from Healthy Cities Illawarra, and I'll introduce our presenter in a moment. I'll just begin by acknowledging the Dharawal people as the traditional custodians on the land I'm coming to you from today. I think so there might be a few different countries joining us. We recognise their continual connection to the land and the waters, and thank them for protecting this coastline, our escarpment and the ecosystems since time immemorial. And we pay our respects to elders past, present and emerging, and any Aboriginal people in the audience or joining us today. So I'll just allow, I think there's someone else needing to come in. No, we're good. So I'd just like to introduce Ty Christopher. He's a former, I'm going to read this because it's a long and impressive bio, a former general manager, asset manager with Endeavour Energy with 36 years experience in the energy industry. Ty developed and implemented internationally recognised processes and results in coordinated infrastructure management, including the introduction of risk-based total asset management approaches. He led the establishment of the New South Wales Demand Management Code of Practice and introduced new technology into the electricity supply industry, such as large-scale battery storage, embedded generation, and digital asset management techniques. Ty is now the director of the Energy Futures Network at the University of Wollongong, focusing on coordinated research into the future of the energy supply. And so in this role, Ty's passionate about reducing customers' energy costs, reducing the carbon footprint of our society, and generating sustainable employment for the clean energy future. So I'll just hand over to Ty. Just a reminder that we're recording the session, so you can share it with friends or colleagues afterwards. And please use the chat, and I'll monitor the chat for questions throughout. And I will now take myself away and hand it over to you, Ty.
Thanks, Kelly. And I feel like I should have told you to just give the abridged version of the intro there, but thank you very much. So, hello, everyone. Good afternoon. My name's Ty, and I'm here to talk today about overvoltage. The hidden electricity thief is the hopefully somewhat catchy title of what can be a dry subject. We'll get into this a little bit in the next couple of slides, but one of the things that I'd really ask everyone to do is to post up your questions in the chat. And what I'd probably like to do is get a little bit way into this presentation and then pause for a check with everyone and perhaps answer some questions, and then we can move on to the rest of it. I have allowed with all of this plenty of time for questions, and I'd really like to try and make this as two-way and interchange as we possibly can. It's always difficult with webinars. I struggle myself not being able to see an audience and interact at the human level. So I'd encourage everyone, please do all you can to chime in. So launching straight into it, with apologies to some of the electrical engineers in the audience, I'll try and explain voltage and what it is, and voltage and current. If we think of electricity flowing as being a bit like water flowing, if you had two buckets of water linked with a pipe, A and B, that you'll see in the left-hand part of the slide, they're at the same pressure level. And so the water doesn't flow between them, it just sort of sits there. As soon as you elevate one of those buckets, bucket A in this case, you've applied a pressure given by gravity in this case, but you've applied a pressure to the water, and that means that it'll flow from bucket A down into bucket B. Now, in electricity terms, that pressure that's being applied is voltage, and you need voltage to be applied to make electricity flow from one place to another. Now, the amount of electricity that flows is measured in amps or amperes, and that's the current that you'll hear people talk about. So voltage is the pressure that makes it happen, and current is the amount of electricity that flows. And then the ultimate result is the power that you use, or the power that's delivered to each of our homes, to each of our businesses. The power is the product of voltage multiplied by current. So the two times together gives you the power that you're using. So as we work through this, it's not meant to be a lecture in any way on electrical engineering, but it's important to understand those principles before we move into why overvoltage that is experienced still in the main by the majority of electricity consumers in Australia, in the national electricity market, is such a significant issue. The other challenge that we've got, of course, with electricity is we can't see it, we can't touch it. That's where it's, most unlike water. And I'd certainly, from a safety perspective, highly discourage anyone from even trying to see or touch electricity. It is quite a dangerous, inherently risky exercise to engage with if you don't know what you're doing or what you're talking about. Now, a graph here to try and explain Australian standards. The voltage that all of our homes should receive and businesses should receive is determined by an Australian standard that has the catchy title of AS 6038 voltages. And prior to the year 2000, that said that the voltage that everyone should receive on average, or the nominal voltage, as you'll hear me use the term, is 240 volts. And in the common vernacular around Australia, and what we're talking about here is quite a uniquely Australian issue, you'll hear people talk about 240 volts. That is the voltage level that comes out of a power point in your average home at a nominal level. But obviously the world is not perfect, so there's a range around that 240 volts that was seen as being acceptable to supply people with, an acceptable voltage range for all of our appliances to still operate satisfactorily. And that range was shown by the bars on the left-hand side of the graph here, and it was called plus or minus 6%. So you could have 240 volts plus 6% or 240 volts minus 6%. Now, that was all well and good, but the reality is Australia was, leading up to the year 2000, different to the majority of the rest of the world that operated these around or above 200 volt systems, in that the majority of the rest of the world actually operates on 230 volts, 230. So the Australian standard was changed. It was changed in the year 2000, 22 years ago. And it was changed to say that the nominal voltage that we should all receive is 230 volts. But it was also acknowledged at the time that you couldn't snap your fingers and instantly change everything, including change the way that this large electricity grid across the country operates. So what was done is an asymmetric or an imbalanced tolerance range was set around the 230 volts. And that's what you see in the middle here. And that's 230 volts is the voltage, minus 6% plus 10%. And as you'd see, that plus 10% on the 230 volts puts you very, very close to the maximum allowable voltage under the old pre-year 2000 240 volt system. And then there was some fudging with Queensland, who didn't come on board with the Australian standard until a couple of years ago. And what we see then is the result of that in the right-hand side of the graph. Still a 230 volt system. Queensland have also then come on board with the Australian standard, but there's now also been a preferred operating range around the 230 volts, and that's the plus 6% minus 2% that has been set. But still, the acceptable range of voltages is right up at that 10% over 230 volts. Lots of numbers and so on and so forth, but what does that actually matter for the Australian electricity grid? What's actually happened is not very much in terms of movement away from 240 volts since the year 2000. Now, that's important, and it's important for all of us, because once the Australian standard changed to set a 230 volt nominal voltage across our country, every single appliance that has been sold in the country and bought by all of us for our homes since the early 2000s, by law, has been required to operate optimally and with most efficiency at 230 volts. And that's what starts to become very important for all of us. If we have a look at where we're at the moment as a country, and there's a couple of figures over on the right-hand side. I don't expect you to, bog down on all the numbers. We'll talk them through. But audits performed by the University of Wollongong through our Australian Power Quality Research Centre, and in particular, the National Power Quality Audit that they undertake annually, show that consistently voltage levels that are received by us as customers are in excess of the 230 volt standard, and usually for a large percentage of the time sit around 245 volts, so even above the old 240 volt nominal voltage level. That's also been backed up by research done by the University of New South Wales, and that research was done on behalf of the Australian Energy Security Board. And the quote from it you'll see here in the slide, but it basically says that people receive, for 95% of the time, voltage levels above and some well above the 230 volt nominal standard as stated in the Australian standard. So we're all getting more volts than we actually need to. Now, what that actually means for us, I'll get to in a moment, but this was the first point where I thought I'd just pause and see if there's anything come through in the chat, or if there's any questions on the fundamentals and whys and wherefores of voltage and the Australian standards before I launch into a discussion with everyone on what it actually means and what it's actually doing for us all. Kelly, is there any questions there come through? No?
There's nothing in the chat just yet, Ty.
Okay, well, that's fine. Let's keep on persisting with what does this actually mean. Supplying voltage at a level that's in excess of what is necessary contributes in a number of negative areas to all of us as day-to-day electricity consumers, whether it's in our homes, in our businesses, or a combination of both. First and foremost, it wastes power and energy on a significant scale. That's been proven, and I'll get into the detail of that in a moment if you like. But even in Australia, there was a sponsored trial from the Australian Renewable Energy Network done by United Energy down in Victoria, and they found that on average, if they reduced voltage by 3%, that it would save between 2 and 3% in the power and the energy used by end-use customers. Another key challenge that's offered by having voltages too high is as we get more and more solar distributed out on the grid. Australia is the global success story for solar and solar uptake, in particular solar uptake on our homes. We have at the moment around 25% of homes that have solar on them, but like all average numbers, that's helpful and misleading in about equal measures, because we do actually have parts of the grid, suburbs in South Australia, and some of them I'm aware of in Western Sydney, where almost every home in that particular suburb has solar panels on it, so approaching 100% saturation. Now, what that means is a solar panel is all well and good for generating electricity. The key component that interacts between the solar panels and the grid is called the inverter, and it sits between the two, and it's the unit that converts the power from the solar panels into the right sort of form that it can then be either used in the home or exported into the grid. Now, when it's looking to export into the grid, a solar inverter has to apply some pressure voltage to get the power to flow out of the solar panels and into the grid in the street. And so what it has to do, that inverter, is ever so slightly, it has to climb above the voltage level that's present in the street in order to allow the solar to actually be exported into the grid. So I presume many of you might start picking up on this now. So picture a situation where you have many homes in the one street all connected to the one set of mains running down the street, underground or overhead, doesn't matter. And each of those inverters is all having to push the voltage up just a little bit so that it can export its power. Sooner or later, you reach the point where you're pushing the voltage too high. And these inverters, these connections between solar panels and the grid, these inverters have an upper limit, again set by another Australian standard, that they cannot exceed. And so what that means is once the voltage in the street has reached a maximum level, not only do you have everyone in the street experiencing a lot more pressure being applied to their electrical appliances than is needed, but you also face the situation where people's solar panels can't export that clean energy into the grid because their inverter is the last one on and can no longer climb over the voltage in the street to allow it to export. So the second major problem with having voltages higher than necessary out there on the grid is what's called the hosting capacity, the ability for the grid to host and bring in more and more solar is increasingly challenged to the point where that clean solar energy will go to waste because it can't actually connect and export into the grid. The other detrimental effect of overvoltage, all of us experiencing this, is a reduced lifetime for all of our appliances. And this is one of the real hidden aspects. And there's research going on into quantifying exactly what this reduced lifetime is, but even the research that's been done to date clearly shows that there is a material and significant detriment to the lives of all of our appliances, whether they're our computers, our televisions, dishwashers, you name it, in our households. That is a direct result of them being constantly supplied at more pressure, at a higher voltage than they actually need. And again, going back to my earlier point that all appliances sold in Australia have been designed to operate optimally and most efficiently at 230 volts. And so feeding them constantly with 240, 245, or even 250 volts, as many of us experience for substantial periods of the day, is shortening the life of those appliances. It could be up to 25%, the early research has shown in some appliances. And then last, but by no means least, applying this greater pressure to all of your appliances, to the grid even, but mainly to all of your appliances, is effectively force feeding them more energy than they actually need to operate. And that excess energy just burns off in the form of heat. If you think about the power supplies and that sorts of thing that feed all of our computers and the like, they're having to choke down this excess voltage that they're receiving so they can just output what the actual appliance needs. And the difference between what's going on there is why they get hot. And so what that heat is, if you can feel it, is I'm reaching across now because there's a phone charger on my right. All that excess heat is energy that we're all paying for that we don't need to. If the voltage was brought down closer to or at 230 volts, the amount of heat generated would be less, and that would mean we would pay less for our electricity bills each and every quarter or whenever, monthly, or whenever you actually receive them. There have been a lot of studies, and the phenomenon that I'm talking about here has a technical name. So this isn't something I've thought of. Don't worry about that. It's called conservation voltage reduction. And so what I do, there's some links here in this presentation, and this can go out there. But if nothing else, if there can sometimes be people who have a foundation level of knowledge of electrical theory who sometimes challenge the validity of reducing voltage, also reducing power consumption. And I will unpack that a little bit in just a moment. But rather than take my word for it or argue the physics of it, the first thing that I say to anyone who wants to engage with this as a topic is please type conservation voltage reduction, the headline of that particular slide, into any of your favoured search engines, you'll immediately be presented with a wealth of information on where CVR, conservation voltage reduction, has been applied across the world, whether it's here in Australia or whether it's in other countries. And the tests that have been done in this, whether they're done in Australia by Endeavour Energy, whether they've been done in the UK, in Electricity Northwest, or whether they were done in Victoria most recently by United Energy, all show that it's not a complete one-to-one relationship in percentage terms. So that, for instance, if you reduce the voltage by 1%, you don't get a 1% reduction in energy. But what you do is you get a reduction in energy that varies depending on the particular types of appliances, types of electrical loads that are on that part of the grid. You do get a reduction in energy that varies between 0.7 and 1%, depending on the type of load. And doesn't sound like much, 0.7, but if you look at the headroom that's there, there's more than enough room for us to be reducing our voltage across the grid by around 5%, which would mean an energy saving for most consumers of at least 4%. And 4% might not sound like much, but across the entire electricity grid at the moment, that equates to around $110 per customer per year forever. And I don't know about any of you, but I wouldn't mind $100 plus off my electricity bill being wiped off and never seen again. So there's some links there, and I would encourage you to have a look at those. Why this varies and why varying voltage doesn't have a one-to-one relationship with energy consumption is there are different types of appliances that use power in different ways. And there are some types of appliances that where you reduce the voltage, they will just put the current up because they want to take a fixed power out of the grid no matter what. And so in those circumstances, you won't see a benefit from voltage reduction. There's a lot of other appliances in our homes that when you reduce the voltage, it keeps the current the same, which means you've reduced the power consumption of those appliances. And that's where there's the benefit to be had from reducing the voltage down to that 230 volts that the Australian standard says it should be most of the time, rather than availing yourself inappropriately of an upper limit that was never put in place for this particular purpose. So if this is all so wonderful, why isn't anyone doing anything about it, is the obvious question I can hopefully hear people being asked. The obvious answers, or the answer why nothing's being done about it, is this represents a bit of a hole in the donut in the way that our electricity market is actually structured. The economic signals to do something about this are very weak. The companies that can change voltage are the distribution electricity companies. That's the network companies, the poles and wires companies, if you hear them mentioned there. And they've got various names. I don't want to start naming them off the cuff here, because if I miss one out, then somebody might be upset. But they are the network companies. They're not the people you pay your electricity bill to. They're your retailer. These are the grid companies that sit in behind that. And they have, if they spend money just to reduce voltage, they do not have, under the existing regulatory regimes, a way to recover that expenditure. And what that means is we have a situation here where the costs of reducing voltage are borne almost entirely by the network companies, and the benefits derived from reducing voltage flow immediately and almost fully to end-use electricity consumers, all of us in our day-to-day lives and in our businesses. And there's a gap between what the regulation allows and whether it's actually looking after the interests, quite frankly, of consumers in this particular space. This is an issue that has been raised with the relevant regulatory bodies. It's been raised by me and other people. And there is some green shoots. There is some action occurring on better voltage management across the grid. Victoria, the Victorian distributors are leading the way in this space. But even then, they are still constrained by how much they can do as a result of the way electricity regulation is structured just at the moment, and this inability for the costs of this to actually be recovered by the people that would spend the money and then let the benefits flow on to end use consumers. So that all sounds like a bit of a disaster, but there is a potential elegant solution for it. And I'm mindful of the audience now, but so in terms of not taking everyone down a rabbit hole in electricity regulation, the national electricity regulations are about 1,000 pages of written material. That's an excellent cure for insomnia, if any of you are sufferers in that space. But there is one piece of electricity regulation that is quite elegant, and it works in all of our favours, probably very much behind the scenes, which is good. And it has the exciting name of STIPUS, the Service Target Performance Incentive Scheme. What it is in straightforward terms is it's a ratcheting scheme that sets targets for any network company based on their previous actual performance. And then if they do better than those targets in a subsequent year, then they're allowed to recover a bit more revenue. If they do worse, then they're penalised and they are not allowed to recover as much revenue or charge as much for their electricity usage. And so it's a good scheme because it keeps everyone honest. And because each year the targets are based on performance the previous year, while a distributor may improve their performance in a given year and be rewarded for that financially, that improved performance now sets where they need to perform the next year. And so in order to get money again, they have to improve their performance again. And this is what I call a ratcheting performance incentive scheme. Now, if you have a look at that scheme, it has a section titled 4, Quality of Supply Component, on page 15, if we're getting very sort of precise about all of this. And on page 15, it basically says there are no power quality measures at this time, to be decided later. If we were to include voltage measurement, voltage quality around 230 volts as a measure in this existing incentive scheme, we would instantly provide a bit, just enough of a financial incentive for these network grid companies to really start to drive voltage down to the 230 volts that the Australian standard says nominally that it should be most of the time. That would then basically mandate a conservation voltage reduction program across the national electricity market and derive for us as a nation and as electricity consumers. For instance, and these are 2019 numbers we're looking at here. So with the way things have gone with electricity prices, these of all the benefits that are shown here would be greater even again now. If we were to reduce our voltage by 5%, which would take us down from our current average of 245 down to around, even 232 to 233 volts, so still above the standard, but not much, it would save just over $1 billion, that's with a B, dollars a year in customer bills across the national electricity market, which through some simple division of the number of customers, $1 billion divided by the number of customers is $108 per person, call it 110 in today's terms. It would permanently remove 1,000 megawatts, which is the equivalent of one coal-fired generation unit, not a whole power station, but one coal-fired generation unit. It would permanently remove that demand from the grid forever, because it's just energy that's being wasted and doesn't need to be generated from any source. It would reduce emissions by around 3 million tonnes of carbon per annum, and it would allow an additional 652 gigawatt hours of solar to be exported on the grid that is currently unable to be exported into the grid as a result of voltage being too high and the inverters that I spoke about earlier not being able to climb over the voltage in the street. So all of those things there could be achieved with potentially a simple change to an existing regulatory regime. And it's obviously a hidden aspect and not something that people are aware of, although that is changing and changing for the better, particularly with the uptake of people with their own solar systems and the visibility through various tracking apps and that sort of thing on your phone that comes with it. But the reality is, as we sit here today and tomorrow and the day after, most of us in our daily lives will receive 240 volts or more. And as a result of that, we'll be using more electricity than we need to in our daily lives. And each day goes past is another day that continues to happen. So I'll end the discussion there. And I should say as well, the branding of these slides, this was a presentation I've also delivered to Engineers Australia at the end of last year, that I've reused a lot of them, and hence you see the sort of the slide branding of them there as well. So happy to pause there for questions. I might, well, I'll stop the sharing if you like, if that's okay.
Yeah, just unmute yourself or put a thing in the chat if anyone has any questions. That was just fascinating. And yeah, I had no idea about any of that. Not surprisingly, that's not my field. But
no, who would? Exactly.
Yeah, and you're right. Like every time I had a question, you sort of soon followed it up with an explanation and an answer. So, wow. So I've got a few questions, but the first one is, so how do you get a blackout?
To your home, what happens with a blackout?
Yeah.
Rightio. Well, a blackout is what I'd call, you know, the binary measure of power quality in terms of it's either there or it's not. And so a blackout can be caused. The electricity grid is layered, the same as a road system and the same as your water supply network. Nobody walks up to the wall of Warragamba Dam with their 1-inch water pipe for their home and shoves it in the wall of the dam. So you need to have a system where you're transporting bulk power from usually its source of creation or generation, major power stations and that sorts of thing, and being able to transport that bulk power like the road network up and down the main freeways and that sorts of thing, the Hume Highway and the like. You then need to break that down for sub-distribution out to major population centres. You then break it down even further to the suburb level, and then it fans out to all of our streets, and then it's broken down again in the street eventually to the should be 230 volt, currently 240 volt plus level of voltage that applies to all of our homes. Now, what that means is a blackout can be caused by a failure or at any level in that particular system. So a blackout could be the transformer that supplies your street and the adjacent streets has had a failure within it. Most often, if you're in overhead areas, something like 3/4, on average, 75% of the unreliability of overhead power networks is caused by trees or parts of trees falling on them and causing a short between, especially a wet branch, between the power lines. Automatic systems that are in place to detect that do so, and like the circuit breakers in your home, trip off the line. The electricity company is then obviously through their control systems made aware of it and can go and dispatch someone to safely remove whatever debris is on the lines and so on. In an underground situation, obviously you don't get trees falling on it, but you do have, in my experience, I've not seen any empirical evidence for it or research, but there is a magnetic attraction between diggers and underground cables. It's the only thing that explains how many times diggers seem to dig up underground cables, even when they know that they're there. So those are the sorts of things that will cause a blackout. The size and scope of the blackout depends on where the fault occurs in the grid and how it how many assets that it actually impacts. Here in the Illawarra, we had a very significant incident just recently at the main grid exit point that supplies our entire region. There was a transformer fire at Yalla. Probably saw it in the news and that sort of thing.
Yeah.
But because that was at a part of the system that has a lot of backup capacity built into it, even that very significant event didn't lead to a blackout because it occurred at a point in the system where it was able to be isolated and there were other assets that could take up the load until it gets repaired. As you move down in the electricity grid, there's less and less of that backup capacity, of course. You've only got one line in your street and then ultimately one cable coming into your home. And a failure anywhere there can give you a blackout.
And so how does all of that relate to, there was lots in the media only a couple of months ago about this energy crisis and the lack of energy on the East Coast. So where was the problem in all of that? Was it the I won't even
that's a huge question, Kelly. That's a huge question. Okay.
Is it real? Because we don't have too much. We've got about 20 minutes, but so
okay, yes and no.
To you just makes me think, there's more.
There's more to this.
Yeah. Go.
Yeah. Okay, so the answer is yes and no. It was we had the power crisis you have when you have plenty of power available. That's the first sort of headline that I'd ask everyone in the audience and everyone to have in their minds. There was and still is today more than enough generation capacity to keep all of our lights on. What we saw, and it's important to sort of put it in this context, what we saw was a suspension of the national electricity market. The failure that occurred earlier this year was a failure of a market design to work properly in somewhat unusual circumstances. Now, if I could go right the way back in all of this, because this is an onion that you need to peel to get to the answer, but I'll be very quick. The short version of it is, it starts with the East Coast gas market, wholesale market for gas, and how it's structured. The East Coast gas market was structured so that it's basically a completely free market. Gas is extracted anywhere up and down the east coast of Australia, and the market it's just free, and the people that extract that gas can sell it to the highest bidder globally, no matter where. And so the price that they charge is determined by gas prices globally, usually. Now, what's happened is Russia's invaded the Ukraine. Western Europe is heavily reliant on various gas resources from Russia. That's affected the market, and internationally gas prices have gone through the roof. What that's meant is the East Coast gas producers are able to sell their gas, and it's cheaper for them, it's still affordable for them to compress it, put it on ships and sail it to the other side of the world. And they're still getting a fantastic price for it. What that means is anyone in Australia on the East Coast that wants to buy gas has to pay that same highly increased price just to get gas that's produced in Australia. It's because when the market was set up, there was never a provision made to reserve a certain volume of gas for domestic use, and to put a price cap of production costs plus profit margin at a capped level on that volume of domestically produced gas, which is what they did in Western Australia. And so what happens is we've now got a huge spike in gas prices occurring here in the East Coast. Now, what happens then is the way the national electricity market now works is its wholesale spot price. You'll hear referred to the spot price. It's determined by whatever is the most expensive generation source that is operating at that 5-minute interval on the grid. So they pick the cheapest, and if they say that, which is usually going to be nowadays solar and wind, and so you say, okay, so all the solar and wind gets dispatched or used first, and if that's enough, fantastic, we're paying a very low price on the spot market for electricity. If that's not enough, you've then got to bring on other generators, coal, gas, etc., to make sure that there's enough energy there to supply all of our needs. What this means is in the daily cycle of things, once the sun goes down, energy prices shoot up because you're almost solely reliant on yes, a bit of wind, but you're heavily reliant on coal and, yes, gas for that evening peak once the sun's gone down every day. So now push that through. What happens when the gas prices have gone through the roof? That means the wholesale electricity prices have gone through the roof, to use my vernacular there as well. And what happened was it reached a point where it exceeded the maximum allowable limits in the electricity market. So the market operator did their job and said, that's it, we're not paying any more. That's the maximum amount we're going to pay, which meant that in particular, the gas-fired generators were going to be paying more for the gas than they could get for the electricity. So they just went, no, we're out of the game. Thank you very much. And then so on, it flowed on to then there was other issues with some coal supply shortages, and there were a number of coal plants that then were not able to bid into the market at that point in time. And so what it was fundamentally was that failure of a market structure to allow for the fact that if generators go into that negative margin situation, they're just not going to offer their services. And when the only other alternatives are variable renewables, which we don't have control over when the sun shines and the wind blows, that's the dynamic that happens. So there's the shortest version I can give of
that's
what
amazing.
happened. Okay.
I don't think anyone would have any idea because, you know, I just understood, oh, we have an energy crisis, and most people understand that that means we don't have enough, whereas it's the opposite, and it's just the market doing its ridiculous thing.
Correct. We've got more than enough. We've got more than enough generators there to generate the power. We've got more than enough gas to power them in that instant when we needed to. It's just the gas is subject to international geopolitics pricing, and the whole house of cards collapsed.
And I've got two other sort of, which I think is still no one's chatting. So I'm taking that they're sort of happy enough with my questions and our discussion. What I was thinking was, so two things. How is the shift to renewables going to impact on this? So if we're getting away from gas and we're shifting to more renewables, how does that work in the grid? And secondly, you know, it just seems like such a strong actual climate change strategy, and I'm wondering how government plays into any control over the electricity regulators.
Sure. Oh, that's a good one. How about I answer the second one first, if that's okay, Kelly? Because one of the key changes that I think that I think is very important is the Australian Energy Regulator has, which is an arm of the ACCC, the Australian Competition and Consumer Commission, and the AER are the economic regulator of the electricity and gas industries. Okay. And the AER have previously sat under the ACCC that would then report to shareholding Minister X at the federal government level, because this is all federally regulated. A significant change that I saw and went, whoa, that's going to get interesting. But as, you know, to non-energy, you know, if you're not a complete energy geek stroke dweeb stroke whatever pejorative label you want to put on me, you think, yeah, so what? The AER have actually been moved out in that reporting line and now report directly to Chris Bowen, Climate Change and Energy Minister. So I think that's very significant. Because when you say, you know, what are the impacts here? So that really draws a hard line of accountability that I think is going to bear fruit for us as a nation. I'm trying to remain politically neutral here. I'm just observing, putting that portfolio alignment to the AER, that could be very, very significant for us as a nation. So that's, if you like, the first question. And there are three, I call them the A team. They don't call themselves that, but there are three energy regulators in the country. You know, one would never be enough. There's the AER, and the Australian Energy Regulator. They look after the economics, all of these markets and that sort of thing. Then there's the AEMC, the Australian Energy Market Commission, they set all the rules, all the technical rules around how things should work. So they're the engineering boffins, if you like. And I say that with affection as an engineer myself. And then lastly, there's the AEMO, the Australian Energy Market Operator. They are the controller, Thomas the Tank Engine-esque controller, who have their hands on all the levers and are responsible for making all of this, both the markets and the physical grid, work and keep the power on as often as it does stay on, which is nearly all of the time for nearly all of the consumers. It's an impressive feat to do that with such a massive piece of machinery. So these three of them, the AER, AEMO and the AEMC, all work in a triangular way between them all. It's all well and good. I think in engineering, a triangle is the strongest structure. In politics, a triangle is probably one of the weakest structures. And I think therein lies the challenge that we have here when we start getting overlaid with some of the political dynamics here. Now, to get back to your first question on renewables, the issues of variability of supply become more and more significant the more and more renewables we get on the grid, because the entire grid does have to balance in real time every light switch that's switched on with every generator that's creating power, whether that generator is a solar panel on the roof of your home or whether it's a large-scale power plant or wind farm or solar farm out west in New South Wales or Queensland. So as we get more and more renewables, what that will create in order for the grid to continue reliable supply 24 hours a day is it will create the need for more and more and more storage, as in energy storage, whether it's batteries, whether it's pumped hydro, where we pump water up to the top of a reservoir and then run it back down again to generate electricity when we need it, whether it's other gravity-based storage systems, whether it's batteries, all of those things will be needed at a scale hundreds, if not thousands of times greater than anything that we've seen to date in order for an increasing renewable percentage grid to continue to deliver the 99.999% reliability that we do actually all experience on average as electricity consumers. And that's not my opinion. That's me repeating what's in the latest released system plan for all of this that's been released by AEMO. Those are their words almost. I'm not presuming to represent them, but that's what they've said in a nutshell. And I think there's the greatest. That's why when you hear so many people talking about batteries, pumped hydro, gravity-based storage, new battery technology, all of these sorts of things, that's why that's so important. Because the more the issue that we've got is we're a blessed nation in terms of the amount of solar access that we've got. The worst solar location in Australia is the west coast of Tasmania. We would never dream of putting a solar farm there. That location is still better for solar output than the best location for a solar farm in West Germany or in Germany or Western Europe. So we've got so much resource there, but the problem is the sun only shines usefully for about 5.5 hours a day. What do you do for the other hours of the day? Similarly with wind. It's variable. So we need ways that we can
store it.
Hoard all of our chestnuts like a squirrel for one part of the day and then be able to eat them on other parts of the day. That's the key to renewables in all of this.
Yeah, fantastic. Thank you so much. It's the last chance for anyone else out there to, I think we've covered so much.
Come on, please, anyone. Voltage geeks in the audience, please speak up now. No questions are bad ones at this point in time. No?
I might throw a question to you then.
Yeah, good on you, John.
Just a quick one around, you were talking about, so there are some things that are very, the voltage and the current of, linked. But
Yep.
things like, you know, are there other appliances, or are there smarts in appliances and their power supplies and in their sort of the way that these devices have been built? And is there a way of understanding beforehand? So for a consumer, would they be able to know whether a device is going to operate appropriately for the appropriate voltage level, or that reducing that voltage is actually going to have a positive impact ahead of time? Or is that just a sort of suck it and see sort of thing? And if your TV breaks slightly later on, then you know that you're right.
Yeah, that's a tough one. So, you know, first of all, obviously the obvious one is, you know, Energy Star ratings give the best indication for any consumers on, you know, what's going to be best in their interest in the long term. Many appliances nowadays, you know, particularly electronic goods, televisions, et cetera, have they have a power supply at the front that, in crude terms, works the opposite way to the inverter on your solar system, in that it converts the alternating current from the grid back down to a direct current to operate the appliance, like the computer I'm speaking at now and many other things. Now, so that will make sure that the rest of the appliance, its life is maintained very well, because it has a fixed output point. The problem is these power supplies are over time overstressed and overheated by an excess voltage coming into them. So one of the things to look at, if you really get down to it, is what is the acceptable operating band for the power supply for any new appliance that you're looking at. And if it's saying it's a 220 volt, a lot of them actually say 220 volt power supply, or they'll accept up to 240, then that's going to have a hard life when it's spending all of its life operating at 245 and 250. And it's going to have a much shorter life than it would otherwise. So picking one that at least says 230 volts is its ideal operating point gives you a little bit more headroom. But, you know, when it all boils down, John, this is the reason why we just need to reduce the voltage across the grid. Because every appliance that we're buying now in our day-to-day lives, by Australian standards and by law, is required to operate optimally and most efficiently at 230 volts. And very few, some of them can tolerate, most of them can tolerate a higher voltage, but ultimately they're designed for 230. And perhaps I should have said earlier in the presentation as well, I mean, there are glitches. If we just wound down the voltage to 230 volts across the board, there's a reason why distributors haven't just done that progressively over time, and that is there will be parts of the grid that when you do that will drop under the minimum allowable voltage from time to time. Now, it won't be widespread. Most of the analysis, and, you know, I've been in the industry for 3.5 decades, most of the analysis and most of what I've seen indicates that only about 5% of the grid would go too far down in terms of voltage if you wound down the sending voltage to be closer to 230 volts. The problem is you would then have to spend money to lift those by augmenting the grid, more poles, wires, or whatever, to bring them back up. And that money would not be approved by the energy regulators, because they would say, well, the only driver for it is because you wound down the voltage, so just put the voltage back up and you don't have to spend the money. That's and I'm not extrapolating there, that's what the AER have said to me. So that's where there needs to be this change, and rather than reimbursement, adopt an incentive regime is what I'd propose is the elegant solution to address these parts of the grid that will have a problem if you wind down the voltage to 230 volts absolutely everywhere. I've tried not to make that overly technical for the audience. I'm not sure that I've succeeded, Kelly. So if we get feedback around those lines, then fair enough. And to everyone that's chimed in here and listened to all of this, thank you. Thank you on behalf of myself. I'm not trying to wrap things up necessarily, but if there are any final questions, I'm happy to field them now. And if not, please, the university, we're always happy to talk to members of the public about any issues energy related.
Thank you so much for your time, Ty, as well, and that amazing level of expertise. I've certainly learnt a hell of a lot, and it's really, I understand a lot more. So thank you very much. And thanks for everyone else for giving up, well, not giving up, you were more enriched for joining us in your lunch hour today. Thanks everyone, and have a lovely weekend.
Thanks everyone.